Buenas tardes a todos. Es un enorme honor para Naturgas Energía, a la que represento, presentar hoy al profesor Frank Wilczek. Profesor Hermann Feshbach, de Física Teórica en el Instituto Tecnológico de Massachusetts. Es un enorme honor porque se trata de una auténtica luminaria en el mundo de la física teórica y sin duda uno de los científicos más importantes del mundo. Hacer un resumen que le hiciera justicia, un resumen de sus méritos y logros, sería imposible en el brevísimo tiempo que se me ha concedido. Con lo cual, pido excusas de antemano porque en la breve semblanza biográfica inevitablemente voy a ser incapaz de cubrir de forma proporcionada los enormes logros del profesor Wilczek. El profesor Wilczek nació en el año 1951. Estudió en la Universidad de Chicago matemáticas y luego fue a doctorarse a la Universidad de Princeton, bajo la dirección de David Gross. Fue en el año 73, trabajando con David Gross, con 22 años, cuando el profesor Wilczek realizó un descubrimiento trascendental que revolucionó la comprensión de las interacciones fuertes nucleares y que constituye sin duda una de las piedras angulares de la construcción del modelo estándar de física de partículas. Se trata de la llamada libertad asintótica. El descubrimiento por parte del profesor Wilczek de la libertad asintótica condujo un enorme progreso en la física de partículas, permitiendo, por fin, no solo una comprensión más profunda de la cromodinámica cuántica propuesta algo antes, sino además la realización por fin de cálculos que permitieran la realización de numerosos experimentos que, por cierto, han verificado perfectamente las predicciones realizadas. Por este monumental descubrimiento, por poner una de las piezas fundamentales de nuestra comprensión actual del universo, el profesor Wilczek, junto con David Gross y David Politzer, recibieron el premio Nobel en el año 2004. No solo el profesor Wilczek hizo un enorme descubrimiento en el marco de las interacciones fuertes y en el marco del modelo estándar, sino que sus contribuciones son variadas y múltiples en campos como la física de la materia condensada o la cosmología cuántica. Y sería extensísimo mencionarlas aquí, aunque uno se siente tentado. Ha sido además receptor de numerosos galardones, no solo el premio Nobel, el premio Lorentz en 2002, recibió el premio de Física de Partículas y Altas Energías de la Sociedad Europea de Física en el año 2003 y el premio Lilienfeld de la Sociedad Americana de Física. No quedan aquí las enormes capacidades del profesor Wilczek. Se ha distinguido también a lo largo de los años como uno de los mejores comunicadores cara a la sociedad de la ciencia. Probablemente uno de los divulgadores de élite de mayor éxito mundial, a través de sus numerosas presentaciones y libros. Esta labor ha sido merecedora también de premios, y tanto en 2003 como 2005 fue considerado el mejor escritor científico de los Estados Unidos de América. En tiempos recientes, y tal vez comunico una primicia, el profesor Wilczek inicia también una carrera en la narrativa convencional y ha terminado de escribir su primera novela. En fin, el ser humano es progreso, es innovación, y la ciencia tiene necesariamente que ser frontera, tiene que ser necesariamente la búsqueda del descubrimiento de lo desconocido. Y de eso es de lo que el profesor Wilczek va a hablarnos hoy, de las fronteras futuras de la ciencia en la que él es una figura fundamental, de las expectativas creadas en física fundamental por la disposición de herramientas novedosas y completamente diferenciales en sus capacidades respecto a las anteriores, como el Large Hadron Collider. Así que, sin más, y con la plena conciencia de haber tenido el enorme honor de estar aquí arriba hoy presentándole, les dejo con el profesor Frank Wilczek. Muchísimas gracias.
Thank you very much. It's lovely to be here, and it's a tremendous tribute to San Sebastian as well as to our hosts and organizers that so many people are ready to come to a kind of scientific event and hear about very difficult and very unfamiliar material. So thanks for coming. This is my first visit to San Sebastian, but I've become a big fan. And I will certainly be voting for you to become the cultural center in 2016. Now, from time to time in the history of physics, there have been golden ages when our understanding of fundamental physics advanced dramatically in a short period of time. During the 20th century, I would say that there were three such periods. There was a period of plus or minus 5 years around 1910, when the theories of special and general relativity were developed. There was a period of plus or minus 5 years around 1925, when the theories of modern quantum mechanics developed. And then there was a theory of plus or minus 5 years around 1972, when the cluster of concepts and models and ideas now called the Standard Model of fundamental interactions developed. So the Standard Model is a very boring name for one of the absolutely crowning achievements of physics and I think of mankind's intellectual development. It gives us remarkably economical and we now know astonishingly precise as well as beautiful accounts of almost everything we know about physics, using equations that are vast generalizations of the equations of electricity and magnetism to also describe the other forces. So, especially the strong force and the weak force are described by equations that are like electromagnetism on steroids. So it would be difficult to exaggerate the success or the completeness of the Standard Model. Experimentalists, since its inception, have been working very, very hard to find discrepancies and flaws. You just heard about another such attempt. But so far, in 40 years of attempts, and success in knocking down the Standard Model would probably lead to a Nobel Prize, or a second Nobel Prize. None of it has happened. The Standard Model has stood up to the most rigorous tests under unusual conditions with the highest precision that we've been able to muster. Nevertheless, we're not satisfied because the Standard Model is not as beautiful as it should be. It's very beautiful, but not as beautiful as it should be, because just because it is so complete and successful, it's close to God's last word on the laws of nature, and we would like that to be a coherent, satisfying, unified picture of the fundamental laws. Whereas the Standard Model as we have it has four fundamentally different kinds of forces: gravity, electromagnetism, and the strong and weak forces that were discovered in investigations in nuclear physics in the 20th century that are more obscure in everyday life but just as fundamental to physicists. And several different kinds of building blocks, electrons, neutrinos, different kinds of quarks, that are not related to each other. Whereas we'd like to have just one force and one kind of building block. So we need to do better. And actually we have ideas for how to do better. I'll describe them a bit later in this lecture in detail. They carry the concepts of the Standard Model, of the symmetry of physical law, a big step further. They explain facts about the world that the Standard Model leaves unexplained. And they would just take our knowledge to a new level and open up new insights into the early universe, new windows into the most fundamental interactions at shortest distances and higher energies. and it would just be beautiful and gorgeous, and we're ready for it. What's been lacking, however, is a way of testing these ideas. These ideas have been mathematically consistent and very powerful and very tantalizing. I'll describe exactly how that works. But we haven't had the tool to really test them. And the reason I anticipate that there's going to be another golden age, the first golden age of the 21st century, to stand beside relativity, quantum mechanics, and the Standard Model, is that finally now the tool to consummate this unification, to see if those ideas are on the right track, is becoming available. And the tool that's becoming available is the Large Hadron Collider, or LHC. So I'd like first to describe what that is as a tangible physical object. So if you fly over Geneva on a clear day, you might be able to see from your airplane a kind of mystic scene like this, with mist and the Alps in the background and Lake Geneva, the city of Geneva over here. And then you look down and you see this very, very strange red ring on the ground. And that's the LHC. Now, I'm joking, of course. You don't see a big red ring. The actual device is 100 meters underground, roughly. But this tracks, and on the surface you don't see anything at all. You just see cow pastures and cows happily moving along and farms. But underneath is, along this path, which is 27 kilometers in circumference, is this big machine. And what's happening in this machine is that protons are being accelerated so that their speed is within a part in a million millions, a part in 10 to the 12th of the speed of light, which is the limiting speed. So very, very close to the speed of light, so that they go around this ring 100,000 times a second, even though it's 27 kilometers long. Protons moving very, very fast, so with unprecedented energies, circulating in both directions. Once you've put in the work to accelerate protons to that energy, you don't want to lose them, so you have them circulate in these rings. And there are two beams moving in opposite directions. At a few points, the beams are made to cross, and at those points, the protons can collide. When they collide, they produce densities of energies that haven't been seen in the natural world, as far as we know, since the universe was about 10 to the millionth of a second old, the earliest moments of the Big Bang. So we're producing little bangs with extraordinary concentrations of energy, but little. They're really little. So it's the density of energy that's high. The actual energy is comparable to the energy of a mosquito flying along. So don't worry about black holes or any of that stuff. Okay, so when you have these collisions, you produce extraordinary conditions, as I mentioned, that haven't been seen in the natural world for a very long time. And then we're going to study what happens under those conditions. Let me say a few words more about how the spectacular engineering aspects of this project, though. To make the protons move around in a circle, particles want to move in straight lines, Newton taught us. To make them go around in a circle, even a circle that's big, that looks pretty much like a straight line, when they're moving that fast, you need very powerful magnets. So the ring underground where the protons are stored is surrounded by very powerful magnets, the kind of magnets you might be inserted into if you were having a magnetic resonance image made of your body, but somewhat more powerful and bigger, and there are lots of them. They go on for 27 kilometers. And they have to be very precisely machined, although they're big because the beam is small, so they have to match up with micron precision. Magnets use energy because they're based on circulating currents which generate heat, and the energy that it would take to run these magnets, if they were ordinary magnets, would be prohibitively large. It would require more energy than the city of Geneva uses, so you'd have to build a special power station. It would be ridiculous. So the solution is to make these superconducting magnets so that the currents circulate without making any heat, without electrical loss. The price of making them superconducting is that they have to be cold. Superconductivity only works at cold temperatures. And so all this plumbing here that you see is to keep the magnets at a temperature which is about 2 degrees Kelvin, 2 degrees above absolute zero. That's colder than intergalactic space, which is filled with the microwave background at 3 degrees Kelvin, or 2.7 actually. So this is the coldest extended region of anything like this size in the entire universe. It's a big job keeping all this working, and you see the heroes who do it get very tired sometimes. You have to imagine 27 kilometers of this stuff, and nothing can fail. To see what comes out of the collisions and interpret it is also a very big job. You have these enormous deposits of energy in a small space. They produce a little bang, and many, many particles come out. I'll show you a picture momentarily. But we first have to discuss how you make the picture. And making the picture involves very sophisticated, gigantic devices, the detectors, that surround the points where the beams cross and the collisions occur. This detector is called the CMS detector, where C stands for compact. This is actually the smaller of the two major detectors at CERN. The Atlas detector is about twice as big in linear scale. You can see the size of the humans here. And it's not only big, but every cubic millimeter of it is meaningful. It's packed with state-of-the-art electronics because you have to be able to reconstruct the paths in 3 dimensions of particles moving very, very fast. You also have to be able to distinguish different kinds of particles one from the other. You want to know whether you have an electron or a muon or a proton. So you have to see how they deposit energy as they travel, how they bend in magnetic fields. All this information is precious to reconstruct the fundamental events that occurred in the collision. I like to say that the LHC is our civilization's answer to the pyramids, but it's much, much better because, well, first of all, it's much, much bigger, but also it's big for a reason. Not just someone's vanity that they want to be glorified, but it's bigger because people are curious. And it's not just bigger, but it's also packed at crucial places with extremely sophisticated devices that are pushing the frontiers even of our modern technologies. So here is a sort of typical outcome of one of our little bangs. Many, many particles of different kinds come out of it. This looks complicated, but actually it's much more complicated than this picture does justice to, because the picture is in 2 dimensions. Actually, these things are moving in 3 dimensions, and that's very important in reconstructing what happened. Also, the picture is a static picture, but we're interested in how fast things are moving, so we actually have to resolve it in time. These things, these yellow lines, as you might guess, are the paths of the particles that emerge. Some of them are moving slowly and bend a lot in the ambient magnetic fields, others are not. To distinguish different kinds of particles, you also want to see how much energy they deposit as they move, and that's what these cubes mean. They're measures of the energy deposit. So it's a tremendous amount of information in these pictures that come out of the detector. Much too much for a human being to analyze, especially since there are millions of them per second when the machine is operating. So the information is fed into a gigantic bank of computers. Actually, most of these things are game chips from electronic games strung together, digital processing chips, because those are cheap and very, very fast, and you can hook them together in clever ways to do the analysis. The project that analyzes the information is called the grid. The grid is kind of like the internet on steroids, because these computers don't just trade text or video. They also trade programs, they trade tasks. They're really wired together as one gigantic computer. What you see here is about one 1,000th of the grid. This is 1/10 of the part of the grid that's at CERN, but there are 100 stations like this around the world, several of them in Spain, that are wired together to make one gigantic computer with cutting-edge computer technology to analyze those complicated events. And it's quite poetic that at the end there's a human being here who looks at what the computer puts out and decides what it means. So I hope that gives you some sense of the LHC as an object or as a project, what's involved in its gigantic and extremely sophisticated engineering. Now I'd like to discuss its purpose, what it does in a conceptual sense. And that's actually quite simple, what it does. What the LHC is an ultrastroboscopic nanomicroscope for studying deep inner space. That is, it's in the same tradition, it's a linear descendant of Van Leeuwenhoek's microscopes that he used to magnify with visible light and discover the cell structure of living things, and of Rosalind Franklin's X-ray images of DNA molecules that were used to decipher the molecular structure that's basic to life. And in fact, that's a very instructive example. If you go back and look up the actual pictures that Rosalind Franklin took, they don't look like pictures of anything. They look like dots. They're diffraction patterns. And you need a lot of image processing and very sophisticated mathematical analysis to turn that into a picture of anything. And in fact, Crick and Watson got the Nobel Prize for turning these X-ray diffraction pictures into meaningful images of actual things in space. The LHC is like that too. We want to take pictures, but much, much, much smaller and much higher resolution in time than even the pictures that Rosalind Franklin took, let alone Leeuwenhoek. So for this, X-rays, photons, the photons of visible light are certainly not good enough. They have very long wavelength and can't resolve details. X-rays, which have shorter wavelength, which Rosalind Franklin used, that can be used for analyzing molecules. Those too are much too big. We need things with nanomicroscopes, so 1 billion times more powerful than a microscope, or 1 million times beyond nanotechnology, whichever way you read it, and also very, very fast time resolution to get pictures that of the most fundamental interactions we're interested in. In effect, what's happening is that as these protons move past each other, they're taking snapshots of what each one is taking a snapshot of what's inside the other. That is, each of them responds to what it finds inside the other one. And so it's taking a snapshot of the conditions in there, but then it's a big job to reconstruct from what we get, these complicated events that I showed you, pictures with many, many things coming out, to go back from that into the basic processes that produced it and get an image of what's inside protons. Now, we don't know what the proton is going to look like when we look at it as closely as we are at the LHC, but we already know what it looks like and what space looks like when you take pictures with about 100 times worse resolution, which is still well inside the size of atomic nuclei, extremely small distances. Things happen very fast in that world, as you'll see, so we also have to imagine pictures that are very much slowed down in time if we want to be able to sense them ourselves. Our eyes were not designed to resolve distances as small as 10 to the minus 15 centimeters or times as small as 10 to the minus 24 seconds. Those kinds of resolutions wouldn't be useful in finding desirable mates or finding edible food or the kinds of things that we were evolved for. But now using our image processing, using our noodles, using our theories and computing and doing a lot of Photoshop, we can reproduce what our eyes would see if they were able to see things that happen that fast on that small scales. So here it comes. This is the deep structure of inner space that you would see if you had much nimbler eyes. So get ready. Here it comes. This is not an artist's impression or a fantasy. This is actually a numerical simulation of what you would see based on our equations of the standard model. And it looks like a lava lamp. What you're actually seeing is fluctuations in the amount of energy in different parts of space that are occurring all the time and very rapidly everywhere. These are the energies in the gluon fields that play a role in holding together atomic nuclei. And according to the rules of quantum mechanics, they fluctuate. They come to be and pass away. These are called virtual particles. So you have these fluctuations in the density of energy. If we were more attuned to the very small and the very fast, to the quantum world, if we had better eyes, this is what we would see. And as I said, the goal of the LHC is to produce pictures with 100 times better resolution and see what else there is that's fluctuating around. We want to look closer at empty space. It sounds like a silly thing to do. I mean, you look at empty space, it's empty. But it's not. In modern physics, empty space is anything but empty. It contains all this structure, all this fluctuations. It's very dynamic. In fact, any particle that exists as a real particle, so any potential building block of matter, any potential constituent of the universe that might have been produced in the Big Bang, also exists in a fluctuating form as these virtual particles. So if we can look very carefully at the virtual particles, we can discover everything there is. And if we look very carefully at space, everything that there is in there in virtual form. The big catch, though, is that you can't just look at emptiness and contemplate it and deduce all of reality. Maybe you can if you're a Zen monk genius. But the quantum activity that I showed you is more like a subconscious thought or a dormant virus or magma sealed beneath the surface of the Earth all these things, unless you supply some energy and take them from subconscious to conscious, or put the dormant virus in a cell so it can start to produce proteins and other viruses, or magma, unless you give it an outlet so it comes to the surface of the earth, they just go back to where they came from and cycle around and don't have any permanent effect. So we have to make those virtual particles real. Let me just say a word about that, with sort of philosophical. In the quantum world, you may be familiar with Heisenberg's uncertainty principle that says if you want to determine the position of a particle, you have to disturb its momentum, so you can't simultaneously describe the position and momentum or position and velocity of a particle. You have to disturb it. Seeing is an invasive process. In the deep quantum world, it goes a step further into the almost mystical. That is, that in the deep quantum world, to see something, you first must make it. Seeing is a creative process, and the LHC is what's going to be able to create our better vision. So, back in terms of this picture, getting a little more concrete, we have these fluctuations. If we manage to supply a lot of energy at the right place at the right time, we can bring this fluctuation into reality and make the virtual particle real. So it's a matter of supplying energy in the right place at the right time to actually see these things. That's why it's to make them real. That's why we create, when we see them, we are actually creating them. They're in our equations, but to make them real, we have to supply energy, and seeing is a creative process in that sense. So that sounds all very mystical, and it is, kind of, and I think that's nice that we get philosophical and different kinds of views from the close study of nature. But it also means something very specific and concrete. For instance, it all comes with equations. That's what I should say. The difference between me and a Zen monk or some mystic declaiming on these things is that I have equations. And I can back this all up with actual equations and calculations. Okay, but in this case, if we want to produce a particle of mass m, say, some new heavy particle that's speculated about in our theories, but we haven't actually observed yet, then you have to supply at least, if you want to produce it as a real particle, since energy is conserved, you have to supply at least the minimum energy that that particle can have. And according to Einstein's theory of relativity, which still looks very good, the smallest amount of energy that a particle can have is when it's at rest, and when it's at rest, its energy is its mass times the speed of light squared. So if we want to produce particles with a lot of mass in a small space, we have to supply a lot of energy in a small space, and that, in short, is why the LHC is what it is. It's a machine for producing a lot of energy in a small space so that we can make wonderful new pictures that are sensitive to new kinds of virtual particles by making them real, by supplying enough energy so that they can tunnel into reality. Okay, so now I've described what the LHC is as a physical object and also as a conceptual object, I hope. Now I'd like to discuss my vision, my anticipation for what I think will be the most significant advances to come out of the LHC. Other people, I should say, have different visions, but, well, naturally I think mine is correct. In any case, it's the one you're going to hear about. So, this is a dodecahedron. It's one of the perfect solids known to the Greeks. There are 5 perfect solids. A perfect solid is one that has all sides the same and all sides being regular polygons, that is, polygons that have all angles and all sides equal. The dodecahedron is a very famous one. It has 12 sides, and all its sides are pentagons. It's very convenient because you can make a calendar from it with 12 sides, and it lies flat on the table and has exactly one side for each month, and probably you've seen dodecahedra like this. As I said, there are just 5 different regular solids, so they're very special. There's a tetrahedron, there's a cube, there's an octahedron, dodecahedron, and icosahedron, and that's all there is. Okay, so knowing that dodecahedra are very special and rare and are based on pentagons and have 12 sides, if someone just handed you this thing, you would know what it is. It's meant to be folded into a dodecahedron. Okay, that's clearly what it was born to do. It has 12 sides. They're all regular pentagons, and they fit nicely into dodecahedron. But suppose some evil spirit had rubbed out part of it, or it had just, over the course of time, been partially erased, and you were handed this thing. Well, now it would be more challenging to realize that what you've got is part of a dodecahedron. But if you had studied regular solids and you knew that there was a regular solid based on pentagons and that you could start to fold this thing up into a dodecahedron, you might think that, well, what I have here is really a dodecahedron that's partially erased. And that would be the right interpretation. Okay, so with that in mind, this is the standard model that I praised to the skies at the beginning. It's based on 4 interactions. 3 of them are shown here that have a strong family resemblance. There's also gravity. We'll come back to gravity later. But this is the strong interaction. I said it was Maxwell's theory of electromagnetism on steroids. The steroids is the 3. That is, in electricity and magnetism, we have one kind of electric charge, and the particles and the photons respond to that electric charge by making forces and radiation. In quantum chromodynamics, the theory of the strong force, we have very similar equations, but on steroids. Now we have 3 kinds of charges that are usually called colors, but they have nothing to do with color in the ordinary sense. They're really charges. And instead of 1 photon, we have 8 different gluons that not only respond to the charges, but can also change one into the other. And in the weak interactions, we have another similar kind of theory, now based on 2 charges. And then finally, there's electromagnetism with its paltry 1 charge that's still there. And these are the building blocks. I said the strong interactions can change one into another, so it changes quarks of one color into quarks of another color. It performs these motions so it transforms among the particles that are horizontally related here. The weak interaction changes 2 different kinds of colors and relates the particles that are displayed vertically here. But you see that the building blocks, even with these transformations, fall into 6 different pieces. So there are 6 different kinds of things that are unrelated by the transformations of the standard model. Furthermore, the strength of this electromagnetic interaction also has to be specified for the different kinds of particles. And these are the average charges that you have to assign to agree with experiment to the charges, to the particles displayed here. I won't say much about it except that these are funny numbers that are only taken from experiment, that have no profound theoretical basis within the standard model. So, as I promised, it's lopsided. It has lots of moving parts. It's kind of embarrassing that it works so well. This is close to nature's last word. No one's been able to find flaws in it. But it's lopsided and has many moving parts. So we're not satisfied. Now, just like in the case of the dodecahedron, we can classify the possibilities for making bigger theories, more symmetric structures that contain the theories we already have. So we had parts of a dodecahedron, we could only have a few possible ways of making unifications into perfect solids. Here, there are only a few possible ways that mathematicians have classified early in the 20th century of making perfect symmetries that, and then we can see which ones might be indicated as completions of the pattern we actually see, just as we completed that maimed dodecahedron by adding extra pieces to make it one of the perfect regular solids. Okay? And of course, I wouldn't be telling you about this if it weren't possible. And in fact, it works beautifully. All the three interactions, strong, weak, and electromagnetic, fit into one unified interaction, which is the symmetry of rotations in a 10-dimensional space. I won't, of course, be able to do justice to this picture, but only I hope you get the impression that it's beautiful. And instead of 6 different kinds of matter that are unrelated, we only have one kind. Every single particle that we know about can be changed into any other particle by the transformations that are in this overlying unified theory. So they no longer are unrelated. They're brothers and sisters. In fact, they're all clones of one another within this theory. And you see all the possible patterns of charges for red, white, and blue colors, and the colors of the green and purple colors of the weak interaction are realized subject only to the constraint here that we have an even number of positive charges. So I won't be able to do justice to this, as I said, but trust me, it's a fantastic, extraordinarily beautiful, and tantalizing correspondence between mathematical ideality, mathematical ideals, and physical reality. If you didn't know the names of these particles, just knowing the mathematical properties that are dictated by the symmetry, you would be able to figure out how they behaved. And of course, the names don't matter, so this really does reproduce everything about the Standard Model, which reproduces everything about physics. Also, those funny numbers from electromagnetism, which gave the strength and used to be unrelated to anything else, are actually unique, simple mathematical functions of these other properties. So we get an explanation of those funny numbers that were dangling in the Standard Model. So it's really extraordinarily suggestive, but when you think about it a little bit, it seems to be obviously wrong. Because there's a reason the strong interaction is called strong and the weak interaction isn't. The strong interaction really is stronger than the weak interaction. Whereas if they were really all unified, one interaction that was completely symmetrical, they should all have the same intrinsic power, the same strength. So this is the way it actually is. The weak interaction has a short range, so but once you get inside the short range, you can compare it with the other interactions, and you find the strongest in strength, and the strongest interaction is the strong one, the weak interaction is a little stronger, and the electromagnetic is the weakest of all. This is, by the way, why atomic nuclei, which are pulled together by the strong interaction, are much smaller than atoms, which are held together by the electromagnetic interaction much more loosely. Okay? I've plotted this funny way with the strongest on the bottom, so it's the inverse strength of the interaction, for reasons you'll see in a moment. Okay, so that looks like a complete disaster. It looks like this tantalizing unification is completely stillborn. Once you take it seriously, you see that it's wrong. But if you think a little bit harder and remember that what we see as empty space is anything but empty, but has all these fluctuations in it, you realize there's a possible way to save the situation. It could be that really the power of the interactions is the same fundamentally, but when we view the interactions through this distorting medium that we can't get rid of, that's empty space everywhere, that it distorts the power, changes the fundamental power, because the power is modified by the effect of all these fluctuations. It's as if we were living in turbulent water with lots of waves. If we tried to form accurate images of small things, we'd have to make corrections. We'd have to put on glasses or something to make corrections so that our vision would be properly adjusted to the medium we're in. So we can calculate those corrections. These are, in fact, exactly the kind of calculations that people win Nobel Prizes for. So you can calculate how the strength of the strong interaction changes as you look at shorter distances or higher energies, theoretically. So we can correct our vision to take away the effect of those fluctuations. And if we do it, we find the strong interaction gets weaker. That's asymptotic freedom. And if you plot it this way as logarithm of energy or logarithm of distance versus inverse coupling strength, you get something that looks like pretty much like a straight line. Okay? So that's what happens to the strong interaction. The part we've actually tested is down here, but nothing prevents us with the stroke of a pen from extrapolating our theory many, many orders of magnitude much further, and following the famous Jesuit principle that it's more blessed to ask forgiveness than permission, we go ahead and try the simplest hypothesis. Maybe it won't work, but we'll have learned something. So now we can test by adding in the weak interactions, and sure enough, they do unify at a sufficiently short distance or high energy. So the different interactions that it looks so different in power at long distances, comparatively long distances, a mere 10 to the minus 14th centimeters where we've actually studied them, look quite different and come to be seen are equal once we make the corrections to see what they look like at a much shorter distance. Now, this may not be terribly impressive to you because two straight lines do tend to meet in a point. Now, actually, things could have gone wrong. They could have pointed in the opposite directions that and then not met, or they could have crossed too early, and that would lead to predictions from processes that don't occur. But still, this is, and by the way, the fact that these are straight lines when you plot this way is a very profound fact about quantum physics. But still, two lines do tend to meet in a point, so this is not as impressive as perhaps it could be. Fortunately, we have three interactions to compare, so we can make a more crucial test. And here it comes. Oh! Not quite. They don't quite cross. They almost cross, you see. They seem to want to cross, but they don't quite make it to unify. Now, what do we do in a situation like this? Well, the philosopher Karl Popper told us that the goal of science was to produce falsifiable theories. If that was really the goal, we could declare victory at this point, because we've produced a theory that's not only falsifiable, but actually false. I mean, what could be better than that? But of course, that's not the way we proceed. If we have a beautiful idea that almost works, we try to truthify it. We try to find ways of making it true. So maybe we haven't been bold enough. Maybe we have not done justice to the full symmetry and beauty of nature. We should look for ways to do even better. And when you think about it, the unification I've talked about so far unifies the different building blocks of matter. So it puts electrons and quarks on the same footing. They can be transformed into each other by the interactions. It also puts photons and gluons on the same footing. They also can be transformed into each other in the bigger theory. And so we have one kind of building block and one kind of force. That's still two things, though. So we have to ask ourselves, can we do this? Consummate the final step in unification. And the answer is it is possible if you use another powerful idea, another powerful unifying idea, the idea of supersymmetry. In the early 70s, before supersymmetry was discovered, the suggestion that there could be symmetries of physical laws, ways of transforming the equations of physics so that electrons become photons and photons become electrons, yet the laws don't change, would have seemed totally outrageous. It would be like trying to say that apples and oranges are really the same thing and can be transformed into each other without distorting the picture. But in the early 1970s, physicists led by Julius West and Bruno Zumino found that there are ways of doing it, and the basic idea is shown here. You introduce a new dimension of space and time, but it's a new kind of dimension. It's not just adding one more dimension of the kind we know about. That would be boring, although people get excited about that too. This is much more exciting. We're adding a quantum dimension, a dimension of a new kind. And what happens when you move in this quantum dimensions are very small. Quanta in general are very small. People talk about quantum leaps, and quantum leaps are meant to be big, but quantum leaps are not big. Quantum leaps are leaps that are so small you can't tell whether they occurred or not. They're uncertain. All right, so anyway, these quantum dimensions, like quantum leaps, are very small. And what happens when you move in the quantum dimension, in fact, is that you don't move at all in a detectable way, but rather you change from one kind of particle into another. You change from an electron or quark-like particle, so-called fermion, into a photon or gluon-like particle, a boson, or if you were the other thing, if you were a boson or fermion, you were a boson particle, so a photon or a gluon, and move into the quantum dimension, you would change into a fermion. According to the idea of supersymmetry, there's this space, this extra dimension of space, that when you move into it, you change from a fermion into a boson, or from a boson into a fermion, and that enables us to unify the different kinds of matter. You can go from one to the other by flipping around this quantum dimension. So they both are incorporated in the same theoretical framework. Now, when you move from one dimension into another, you change from a boson into a fermion or vice versa. However, some things stay the same. Electric charges stay the same. The weak interactions and strong interactions stay the same. So that, for instance, when we have the supersymmetric partner, the superpartner of the electron, it becomes something called the selectron that hasn't been observed yet, hasn't been discovered. It's theoretically predicted. That would have the same electric charge as the electron, but zero spin and no strong interactions and weak interactions that parallel those of an electron. So we'll be able to recognize these particles if they exist. We'll be able to recognize them when we see them because we have pretty definite ideas about their behavior. So together with electrons, there are selectrons. Together with gluons, there are gluinos. Together with muons, there are smuons, they're called. Photon, photino, and so forth. You also have the rock star Pedro and Super Pedro. So you have these apples and oranges, and now we've discovered that if you allow yourself the freedom to maneuver in superspace in this quantum dimension, move around, you can flip one into the other, and now we know how to change apples into oranges and oranges into apples. And it's really fun and easy once you know how to do it. So. Okay. Now, to consummate this idea, we need, together with the electron, we need this new particle that hasn't been discovered, the selectron, and the other new particles I mentioned. So there are lots of new particles. And as I told you before, whenever you have a new particle, it also exists in its virtual form. So there are new fluctuations that have to be taken into account, things that weren't in that picture I showed you before that would show up at higher resolution. Those fluctuations also distort our vision. So if they also exist, we have to make a different calculation to correct, to see what the basic interactions look like at shorter distances. So we can do that calculation, and if you do it, you find an astonishing result that now the different couplings really do meet within the errors of theory and experiment, which are the width of these lines. So it's really tantalizing. So if you put together both ideas of unifying the different interactions and unifying the different kinds of bosons and fermions, then it really all clicks together. And as a bonus, totally unanticipated, gravity, which so far we've neglected, at the level of an interaction between elementary particles, is extraordinarily weaker than the others. So it appears to be hopeless to try to unify gravity with the other interactions. If I tried to put gravity on the same scale at the sort of energies and distances where we've actually measured things, you can see that the strong and the weak, the electric forces differ by about a factor of 10. So maybe gravity would be another factor of 10, which would put it up above the screen here a bit. But actually that's not good enough. Well, maybe it's another factor of 10. That would put it higher in the building somewhere, or that's not good enough. You might try another factor of 10, then you're in the atmosphere. Or another factor of 10, you're starting to escape the atmosphere. Another factor of 10, another factor, start to escape the solar system. You have to do it 40 times before you reach the strength of gravity. Gravity is 10 to the 40th times weaker than the other interactions, say, between protons. It's really, really, really weak. So when I plotted this, I had to go outside the known universe to start the graph for gravity. But I was very persistent, so I started outside the known universe, but continued the calculation to higher energies, and gravity responds directly to energy, so it changes very rapidly and becomes stronger as you examine interactions at higher energies. And by golly, if you just have the patience and courage to continue this calculation, it does seem to unify also with the other interactions, whose unification was calculated on a totally different, independent grounds. So it's really, really tantalizing. You might want to say, and I will say, that supersymmetric particles have been discovered virtually discovered, because they've been discovered as virtual particles. Now the challenge is, can we make them real? Because otherwise they're just a little too fantastic. Well, if they're going to do this job of making big distortions in the way the couplings change, they can't be too heavy. In fact, they can't, because then the fluctuations, if they were too heavy, would be too small. They would occur only at too short distances. So, in fact, they can't be so heavy that they would have escaped detection at that they will escape detection at the LHC. The LHC will have enough energy to produce some of these particles if they exist and if they do this job. So there's going to be a trial by fire based on the question, do supersymmetry's new particles show up at the LHC? If not, In the trial by fire, everything I've told you goes up and nothing is left. But if we're lucky, we've heard this siren song of symmetry. I worked very hard to swim ashore. We've left behind the comforts of our ship, the Standard Model. And here we are. Nature sung a siren song. Here's nature. Here I am. And we'll see. So it might go all up in smoke, but maybe, if we're lucky, if I'm lucky, when this job of analyzing the stuff that comes out of the little bangs is done, we'll find some events, once in a while, 1 in a million, 1 in a billion, actually, is the kind of thing we're looking for, where there's something that is not in the Standard Model. There are particles that don't fit into what we know already. And they'll say, here I am, I'm a selectron. Here I am, I'm an anti-selectron. And then, then we'll have arrived at the golden age. So it's an exciting time to be a physicist, and thank you for your attention.